Hello, good morning. So let us continue our discussion on computer organization architecture. So for today, we will discuss the embedded systems. Oh, 7 slides na lang pala to. Anyway, again, without further ado, let us continue. So basically, the term embedded system refers to the use of electronics and software within a product as opposed to a general purpose computer such as laptop or desktop system. Examples include cell phones, digital cameras, video cameras, calculators, and many more. And numerous types of sensors and actuators in automated systems. So itong embedded system na to, unlike laptop and desktop systems na pinagsasama-sama, dito sa embedded systems, nasa isang board. No? For example, ang binigay sa atin is yung cellphone, di ba? Sa hardware niya, meron na siyang kasamang software, meron siyang kasamang mga meron siyang iba't ibang kasama ng transistors, di ba? LCDs, meron na siyang mga batteries, di ba? Magkakasama na. At the same time, meron na siyang mga operating system, may mga firmware na siyang kasama, no? Wherein, pagka mag-update ka, nandun na, no? So, aside from cellphones, meron ding binigyan na example dyan, yung cameras, di ba? Yung camera, meron na siyang hardware doon, meron na siyang software doon, may electronics na rin siyang kasama doon mismo sa product na yon. Okay? Refers to the use of electronics and software within a product. Okay? So, aside from that, mga calculators, home security systems, di ba? Yung mga Wi-Fi mesh natin, for example, yung Google Mesh, yung Amazon Echo, di ba? So, those are some examples of embedded systems. Okay? Meron siyang iba't ibang sensors, meron siyang iba't ibang actuators, and those systems, again, have been automated in such a way. Okay? Unlike laptop na pinagsasama sa desktop, pinagtatagpitagping pyesa-pyesa, but yung embedded systems, nandun na, sama-sama na. Okay? So here's in the right side, on the right side of my presentation, you can see the possible organization of an embedded system. Okay? So, nandiyan pa rin si processor, CPU. Lahat naman ng embedded systems, meron siyang processing unit. Okay? So, here's the architecture, no? Connected dito sa processor, meron siyang logic, meron siyang memory. Of course, may memory siya, no? May mga ports na kung saan doon mo nilalagay yung mga serial bus mo, mga cables mo, no? Meron din siyang digital to analog converter, meron siyang analog to digital converter. So sensors and actuators. So sensor, di ba? For example, meron kang movement. Bigyan ng example cellphone, di ba? May sensor siya na kapag may katawagan ka, nakaganyan ka, tumawag ka. Na-sense niyan, nakadikit yung screen na salamin sa tenga mo, di ba magdidim siya, magda-dark siya. So that's actually a analog to digital converter. Ayun, AD. Yung digital to analog converter naman, meron tayong actuators and indicators. Ano ba maganda example dyan? Digital to analog. Yung mga cellphones din, di ba? From digital siya, from ones and zeros na nakasave sa laptop, sa cellphone mo, conversion siya into sound, di ba? Into voice, kumbaga, ako sana. So that's, aside from that, may human interface. Hindi naman pwedeng, wala kang human interface. Paano mo siya ma-update? Paano ka makapag-code? For example, paano mo ma-update yung system kung walang human interface? Paano mo i-update yung firmware ng iyong analog to digital converter? Diba? Paano mo i-update yung firmware ng sensors mo kung wala kang human interface? Diba? And these are the organizations of an embedded system. No? So again, embedded system refers to the use of electronics, no, and software within a product. So now let us discuss microprocessor and microcontroller. Okay. As we have seen, no, early microprocessor chips includes registers, an ALU, and some sort of control unit or instruction processing logic. No? As transistor density increased, it became possible to increase the complexity of the instruction set architecture, or ISA, and ultimately to add memory and more than one processor. Contemporary microprocessor chips, as shown in figure 1.2, include multiple cores and substantial amount of cache memory. Sabi 1.12 natin. 1.12. Hindi ko pala naipakita 1.12. Ito, you can get this an example. No? Ba't ibang processor chips siya magkakasama dyan, no? Diba? Ano ba to? Figure 1.2 pala. Anyway, yeah. A microcontroller on the other hand, no, makes a substantially different use of logic space available. No? In 1.15, ito, 1.15, no? Shows in general terms the elements typically found on microcontroller chip. As shown, a microcontroller is a single chip that contains the processor, non-volatile memory for the program, or ROM, ROM na tinatawag, volatile memory output for input and output, yung RAM, tinatawag, random access memory, a clock, and an I/O control unit. The processor portion of the microcontroller has much lower silicon area than other microprocessors and much higher energy efficiency. Okay, so let us discuss the difference between microprocessor and microcontroller. Okay, when we say microprocessor, meron siyang registers, meron siyang ALU, and meron siyang control unit. Yung microcontroller, kompleto na siya. Okay? Yung microprocessor kasi, ang meron lang siya dyan is yung control unit, ALU, and control, processor, and ALU. Nagpa-process lang siya ng instruction. On the other hand, yung microcontroller, it's like a small size PC. Why? Kasi, meron na siyang RAM, though meron din naman si microprocessor, but mas marami ng chips na nasa loob ng microcontroller. Meron na siyang input-output, meron na siyang serial ports, parallel ports, meron na siyang mga converter na kasama, and timer or yung clock na tinatawag, no? So mas marami na siyang chips na nakasama sa microcontroller, unlike sa microprocessor which wherein ang ginagawa lang niya is it process unit, meron siyang control, ALU, and registers. Sa microcontroller again, meron na siyang RAM, may ROM, may I/O na siya, may clock na siya. It's basically a small computer na. Okay? To give an example of a microcontroller, Arduino, di ba? We bought Raspberry Pi, di ba? Yung microprocessor naman, yung chip na nag-iisang ganon, the Intel Core i9, AMD, ano ba yung mga versions ngayon ng mga CPUs, no? So, yun ang kaibahan ng microprocessor sa microcontroller. Okay? Later on, panoorin natin kung ano bang kaibahan ng microprocessor sa microcontroller. It will be explained by a computer engineer as well. Mamaya panoorin niyo. No? So, let us now discuss the microprocessor speed. Ano ba itong tinatawag ng microprocessor speed na to? Okay? So, meron tayong iba't ibang considerations or key aspects or key areas for us to know or for us to overclock, yung mga overclock na tinatawag, no? Or to maximize the speed of our microprocessor or ng mga CPUs natin, no? We have the pipelining, branch prediction, superscalar execution, speculative execution, and data flow analysis. So yeah, I have included here the some YouTube videos that we can watch. Okay, So again, let us first discuss what's pipelining. When we say pipelining, it enables a processor to work simultaneously on multiple instructions by performing a different phase for each of the multiple instructions at the same time. The processor overlaps operations by moving data or instructions into a conceptual pipe with all stages of the pipe processing simultaneously. So meaning, lahat ng instructions, regardless kung ano pa man yan, pagsasabi-sabi niya ng gawin, tatrabaho niya na sabay-sabay. No, regardless of mga ano ba itong phase 2, phase 3, phase 4, phase 5, kahit anong phase pa yan, pagsasabi-sabi niya ng gawin yung instructions na yan, then ipapasok niya sa isang pipeline, diretso labas na ng, diretso decode and execute na ng instructions yan. So that's pipelining. It enables the processor to work simultaneously. Okay? Simultaneously, ibig sabihin sabay-sabay. On a multiple instructions by perform different phases at the same time. Somehow, sabi nga niya, the processor overlaps operations. Kasi nga nagkakasabay-sabay, magkakaroon talaga ng overlapping yan. Okay? So paano ang paraan? By moving data or instructions into a conceptual pipe. So that's pipelining. Okay? Later on, makakapagbigay tayo ng example. Makakapagbigay tayo ng example sa papanoorin natin. The next one is the branch prediction. Ano naman ba yung tinatawag na branch prediction? Basically, the processor looks ahead in the instruction code fetched from the memory and predicts which branches or groups of instructions are likely to be processed next. If the processor gets right, but again, most of the time, na tama yung kanyang guess, you can prefetch the correct instructions and buffer them so that the processor is kept busy. The more sophisticated examples of this strategy predict not just the next branch but multiple branches ahead. Thus, branch prediction potentially increases the amount of work available for the processor to execute. Okay? So unlike pipelining na pinagsasabay-sabay lahat, yung kahit anong phase ba siya, sabi yan, multiple instructions, nagkakaroon na ng overlapping sa mga pipes by moving data and instructions. Sa branch prediction naman iba. Sa branch prediction, forward-looking si processor. So paano forward-looking? Okay? So yung mga instruction code, pinipredict niya na ano ba yung groups of instructions na pwedeng makasunod, may sunod sa mga process or sa instructions na in-execute. Okay? Because of the formula, kay Little Law yata siya, there are tendencies na maraming correct guess si processor. Kaya lahat ng instructions niya is okay, na totally sabay-sabay, but in a proper sequence na. In a proper order na. Okay, unlike sa pipelining na may overlapping, dito is may mga buffer na sunod-sunod na yan. Nakapila na, for example, 1, 2, 3, 4, 5, 7, 8, 10. Nape-predict ni processor kung ano ang possible na sunod na phase, sunod na instruction, kaya okay na yan. Okay? The more sophisticated examples of this strategy predict not just the next branch or the next step, but multiple branches ahead. So dito, kung speed ng processor mo is gigahertz na, mas mapapabilis, mas maganda yung sequence, yung order niya, mas okay na. Tsaka kung okay yung order ng instructions mo, mas mabilis nga yung pag-execute ng mga instructions. Branch prediction potentially increases the amount of work available for the processor to execute. Okay? So here's an example of microcontroller chip. Di ka kasi naipagkasya kanina doon sa slide. So in a microcontroller chip, meron tayong iba't ibang IOs, iba't ibang chips na kasama na. Okay? Ano ba yung mga yun? May converter tayo, meron tayong mga IOs, may bus tayo, bus USB ports, meron tayong mga regulators, frequency, Mapapansin nyo nga sa may Arduino, di ba? Meron siyang mga pins, input, outputs. Meron siyang processor sa gitna. Meron siyang, anong tawag doon, parang yung cord, anong tawag ito, yung USB port. Di ba? Ngayon yata Type-C na. Tapos, meron siyang mga GSM module, Wi-Fi module na nakasama doon, di ba? So, that's a microcontroller. But yung microprocessor, ito lang siya. Ito, kung nakikita nyo itong screen ko, ito lang microprocessor. Ang meron lang siya is sequencing logic, ALU, and the control unit. Some other microprocessors, katulad ito, meron na siyang iba't ibang memory, cache na tinatawag, di ba? So that's the difference between microcontroller and microprocessor. So, yeah, I have here 3 videos for us to watch. The CPU pipelining, and branch prediction. So yeah, it can consume 50 minutes of our time. I think wala nang problem doon. I think, yeah, mamaya natin panoorin yan. So ito naman, superscalar execution. No? When we say superscalar execution, this is the ability to issue more than one instruction every processor clock cycle. In fact, multiple parallel pipelines are used. So, kung pipelining is one pipeline at a time, dito naman sa superscalars, multiple pipeline, no? Multiple pipelines are used. Okay? Pero at the same time, overlapping pa rin siya. Overlapping pa rin yung instructions niya, yung decoding niya, yung executions niya. Okay? So, speculative execution on the other hand, it uses branch prediction and data flow analysis. Some processors speculatively execute instructions ahead of their actual appearance in the program execution, holding the results in temporary locations. Yan ang purpose kaya meron tayong memory and RAM. It can restore temporary executions. No? This enables the processor to keep its execution engine as busy as possible by executing instructions that are likely to be needed. Okay. Oops, medyo maliwanag yata. Okay lang yan. Yeah. So data flow analysis, the processor analyzes which instructions are dependent on each other's result or data to create an optimized schedule of instructions. In fact, instructions are scheduled to be executed when ready, independent of the original program order. This prevents unnecessary delay. It is somehow related kay branch prediction. Kasi, makikita nyo, dependent naman sa instructions. Okay, kung anong next na pwedeng isunod sa yung set of instructions yung gagawin niya. Diba? So I think we can watch the following videos. No? I have 2 slides remaining na lang din naman. Okay? Embedded system microprocessor. Yeah. Let us watch the 5th video.
The history of the computer. That little chip in your computer, yeah, it's complex, but it manages that complexity in an incredibly elegant way. Today, we explore just one aspect of how it does that. I think even among those of us who aren't particularly tech savvy, we would probably have heard of the CPU, the central processing unit in your computer. We probably have some impression that it takes in data, does some calculation and stuff, and that's where the magic happens. Well, that's a fairly good start to understanding the CPU. I think we can afford to delve a little further today to better see how tasks are being managed by the CPU, as well as to consider how it interacts with the rest of the hardware in your computer. Today, we'll speak in very general terms, not focusing on any specific CPU architecture. Instead, I just want to focus on one specific optimization technique that I find interesting. As we go through today's concepts, you may find that you are already familiar with some of them. Good for you. Feel free to skip ahead by using the links in the video description or by using the chapters on the seatbelt. Let's start with CPU basics. We know that your computer runs programs. At a lower level, these programs are essentially instructions, simple steps expressed in the language of hardware for your CPU to understand and execute. Here's the interesting thing. Most instructions aren't done instantly. Each step can be broken down further into subtasks that are common to the processing of many of the instructions. One basic 5-step model to explain this is fetch, decode, read, execute, write back. What you find is that to execute any instruction, some combination of these 5 subtasks must happen. Here's what they mean. Fetching involves pulling the actual instruction out of RAM, that is, the random access memory of your computer. Yeah, instructions don't just fall into your lap for free. The CPU must fetch them. Then, the decode step is where your CPU tries to understand the instruction. Typically, instructions are just big numbers. If you break it down into its binary representation, different sets of bits represent different things. For example, the number represented by the first couple of bits could be the opcode, that is, the number representing the operation to be done. It could be arithmetic, like addition, logic, like comparing two numbers, or even reads and writes to RAM. The rest of the numbers are the operands to that operation. The decode step is pretty much mandatory to understand exactly what your CPU is supposed to do. The read step involves fetching the required operands in which the operation is meant to act on. For example, if you have an addition operation between two numbers held in two registers, that is, little banks of memory that live directly on the CPU, this is where we visit the two registers to retrieve those values. Now that we know what we want to do, and we have the required information to operate on, we can proceed to the execution step. That is when the operation is actually done. So whatever calculation or comparison takes place, and the result is ready for the next step. Finally, there is write back, in which the result is stored somewhere. This could be back into the registers or even to RAM. It wouldn't be amiss to imagine these subtasks to be different stages on a pipeline, and every instruction needs to go through all of these stages to be executed to completion. So this breakdown, this abstraction, is a great way to think about exactly what a CPU does. However, in doing this, we also start to see an interesting flaw. While yes, an instruction must go through every pipeline stage, let's shift our attention to the other stages as an instruction is moving through the pipeline. Notice that more often than not, the other pipeline stages are idle. While an instruction is being executed, the fetch, decode, read, and write back stages are just sitting there. As you can imagine, it would be horrible for performance if, at any given point in time, only a fifth of your CPU is really doing anything. We're not making good use of resources this way. But here's the good news. We can do what is known as instruction level parallelism, which is fancy speak for saying that we don't really have to wait for one instruction to finish up before starting on the next one. You see, the beauty of this pipeline is that the stages are independent of each other. For the most part. In fact, we'll get in trouble for this, but let's save that for later. Assuming then that the steps are completely independent of each other, we can absolutely send in a second instruction while the first one is still being worked on. What this means is at any given moment, if you were to look at the pipeline, you will see that every single stage is hard at work. But the beauty of this is that each stage is working on a completely different instruction. Every instruction still needs to move through the entirety of the pipeline, of course. But by not waiting and moving straight on to the next instruction, we eliminate idle time. Alright, where's the catch? In an ideal world, this would just work. But unfortunately, certain combinations of instructions back to back could create some unexpected problems. We call these hazards. Let's say we have these two instructions one after another, and I'm going to use simplified instructions here to make things easier. Imagine W, X, Y, and Z to be some registers on the processor. Intuitively, what we'd expect to happen is Y and Z are added together and stored in X. Then, we make a copy of X into W. However, if these two statements were run one immediately after the other in a pipeline, what would happen? Let's find out. Assuming we're still sticking to the 5-stage pipeline described previously, here's what's going to happen. If the first instruction starts at t equals 0, it's going to do its magic and write the answer into register X by t equals 5. Now consider the second instruction, which needs to read off the value of X. It has to do this by t equals 3. That's where its read stage is. We should be done with the entire calculation by t equals 5. But the value of X is only available at t equals 5. I don't know what the second instruction is reading off, but it's not going to be correct, simply because the correct answer isn't yet ready. The formal name for this is a read after write hazard, because that's exactly what happened. We're reading immediately after writing, and we're not ready for that. So how do we deal with this problem? There are several strategies that are relevant here, the simplest of which is a pipeline stall. We simply wait. If we know that information isn't going to be populated in time, we simply pause the second instruction. It will sit around and wait until the data is ready, then it continues. Well, very simple to discuss and implement. The drawback, of course, is that we now have these bubbles in the pipeline. The whole reason why we want to do pipelining is to avoid idle moments, and adding a stall sort of flies in the face of that. Of course, the hope is that hazards don't crop up often, so this will still, statistically at least, be better than no pipelining at all. Of course, more sophisticated strategies can be employed here. One such solution is operand forwarding. Think of this as a secret passage that connects different pipeline stages together. Information can take the shortcut and jump to a later stage ahead of time. Let's try the same example using the same pipelining model as before, but now imagine there is some means of communication going from the execute stage back to the read stage. The second instruction still needs a stall at t equals 3. You can't avoid that since the answer hasn't been calculated yet. However, we can avoid waiting for the callback if we simply send that answer along that secret passage to the read stage at the very moment in which it's ready. Thanks to this, we only need to stall for 1 unit of time, and the two operations now finish at t equals 7 instead. Alright, let's throw another instruction into the mix. Let's say now our instructions looked like this. Here's what would happen if we executed them faithfully step by step. Because of the stall in executing the second instruction, the third one couldn't simply power its way through, so it needs to stall as well. Thus, you can imagine how a stall creates this cascading effect until that bubble disappears entirely from the system. But here's the thing, do we really need to do that? If you take a closer look at the third instruction, you'll find that it's completely independent of the two preceding instructions, in that it doesn't rely on W, X, Y, or Z. This is important because if an instruction is completely independent like this, we don't actually have to run it in order. Try this. Let's swap the order of the second and third statements and see where this gets us. Since the new second instruction doesn't really care about the first, we can push it into the pipeline and let it run to completion by t equals 6. Now, the third instruction kicks in at t equals 2 with its read stage slated to kick in at t equals 4. Let's say our operator forwarding is still active, so the result of the execution of the first instruction at t equals 3 gets pushed directly to the read stage of the third instruction. No stall required, it just picks up and carries on, finishing all 3 instructions in 7 cycles. That's right, by just executing the instructions out of order, we eliminate even the last stall, making full use of our CPU with no idling at all. Of course, as you can imagine, putting instructions out of order is a delicate thing to do. We have a very contrived example here, but in reality, variables and lines of code affect each other in complex ways that mean we may not be able to reliably reverse their order without creating weird problems down the line. CPUs must be smart at determining whether statements are dependent or not before carrying out such an optimization. So far, we've considered sequential instructions, and that's already a can of worms sometimes. But get ready to open an even bigger one when we introduce branching. If statements and loops both cause your code to jump from one instruction to another, and oftentimes this jump is based on a condition. Let's start by seeing what that looks like in the pipeline before taking a closer look at the conundrum it creates. Take for example a simple conditional jump, say at the end of a countdown loop, in which we'll jump back to the start of the loop if the loop counter is still greater than 0. A typical instruction used in this context will be along the lines of branch if not 0. Its parameter would be whatever register the loop counter lives in. What does that look like in the pipeline then? We need to fetch and decode this instruction to know that we want to do a conditional jump. We then need to read off the parameter, then execute the comparison before we can actually conclude whether we should jump away or simply fall through and continue on. That's not too bad, but what about the rest of the pipeline? In the 4 cycles it takes to decide whether or not to jump away, we've still got to load things into the pipeline. But the question is, where from? If we're jumping away, we should start loading the pipeline with instructions from the destination of the jump. Conversely, if we're staying put, we should just load up these subsequent instructions. But the thing is, we don't know, do we? We can only guess at whether the branch is supposed to be taken or not. If we guess wrongly, we end up loading up a set of instructions that were never meant to be executed, before we realize we're wrong. At that point, we've got to throw everything out in what is known as a pipeline flush. This of course sets us way back, much worse than a stall does, since we are starting from a clean slate and have to load up instructions from scratch. So the thing is, we also have to be kinda smart about how we predict whether a branch is taken or not. In the previous example, if we know that a branch is used in a loop, then it probably makes more sense to just assume it's taken. We'll be wrong once at the time in which the loop exists, but that's the safer option because the alternative, which is to assume the jump isn't taken, is going to be wrong for every iteration of the loop except the last one. The thought process here is what is called branch prediction, and it turns out that there are many strategies out there for doing this. These processes are generally what's known as heuristics, which is a fancy word for saying, we're just guessing. Of course, the better the heuristic, the more likely it'll be correct. At its simplest, static branch prediction is used. These just look at individual instructions as they come along and apply some rule-based strategy to guess at whether the branch is taken. For example, the CPU can decide that all backward branches are not taken and all forward branches are taken. Of course, this has to match the way in which the programs are written for best results. CPUs can also use random branch prediction, leaving things to a game of chance. By randomly deciding whether or not branches are taken, it aims for the perfect middle ground of 50%. Then there is dynamic branch prediction, which is the most interesting of all, since it employs some strategies to learn over time. By recording whether or not past branches are taken, it can use that track record to factor in whether or not the next branch is likely to be taken. Such strategies can get complicated, utilizing additional memory, perhaps having a table somewhere, or even loading up multiple instructions in blocks to analyze them. Some CPUs employ multiple sets of branch predictors, perhaps tuned with different priorities, say one to be quicker and the other to be slower but more accurate, and the two have to duke it out. And of course, in this age of AI, some CPUs are even using neural network-based methods. And that's it. Today we looked at a simple model of a CPU pipeline to see how it helps us with parallelism. We saw that while this can help keep every part of the CPU busy, the drawback is that weird things like hazards can happen. This gets worse when branching is involved because we are at risk of loading up the wrong thing and having to flush it all out. The amount of optimization that goes into designing a commercial product like a CPU is astounding. We've barely scraped the surface and, to be honest, we've glossed over all the nitty-gritty implementation details.